Okay, so what we'll now do is go through some examples. So here is and what we saw until now is kind of we covered also in 228. So now what we are going to start seeing is going to be only it's not was not seen probably last time. So start focusing more closely. So things will start deviating from now. So given a polynomial. Okay, so let us use examples to understand the theory. So given a function f of n, what we want to do is we want to find a function g of n such that f of n is big O of g of n, or f of n is state of g of n. So this could be the nature of the problem. I'll give you one function, the f of n function. You want to find a g of n function such that f of n is big O of g of n, or f of n is state of g of n. So in this case, I want to find a function where f of n is big O of g of n and is definitely should not be theta of g of n. You know, big O need not imply theta. It could imply theta, but need not imply theta. And in this case, yes, it should not imply theta. So you want to choose a g of n function in such a way that it can be written only as f of n is big O of g of n and not as theta of g of n. So that means an initial guess is you could pick something greater than 3. If you pick something for g of n whose degree is also 3, then we can say f of n is theta of g of n. So we should pick a function for g of n whose degree is greater than 3. So I can pick g of n to be n to the power 4. So this is kind of like just looking at the function, we made kind of intuitive analysis and came up with g of n function. So now what we want to prove is prove this. Okay, so prove that I can pick a function g of n is n power 4 such that 5n cube plus 6n plus 2 can be written as big O of n to the power 4. How you mathematically prove this? So from now in this module there will be more math. So we'll go through kind of slowly, but I'll go through the steps, and I think I have covered, typed up all the steps as much as possible to make it easy to explain. Okay, all right. So let us go through this. So the approach we are going to use is this limit approach. Okay. So what we'll do is, so given two functions, say f of n or t of n, and then this g of n, we'll take the ratio of these two functions and evaluate this ratio as this n tends to infinity. You may already know we call this notations big O theta as asymptotic notations because we are worried about the time complexity as n grows larger. That means as the input size gets larger. So the input size is n. So as n tends to infinity, how these two functions are related to each other. So as n grows to infinity and the ratio of these two functions is 0, that means, like, think about this, you have a small value in the numerator and then divided by, say, a very large value. So this ratio value will be close to 0. Right? So this is very close to 0. So this is what I mean here. If you have a function t of n, which is like this 2, and g of n, which is like this denominator value, and if the ratio tends to 0, that means the denominator function grows faster. It means it has a very it grows quickly compared to the numerator function. So the numerator function grows slower as n increases, whereas the denominator function grows much quickly as n increases. So if you want to relate the two functions t of n and g of n, which is the numerator is this t of n function and the denominator is this g of n function, then how can the two functions be related? The g of n is the big guy here because it grows faster. So the faster growing function goes inside the big O notation. The function whose values grows quickly as n increases goes into the big O notation. So we can say T of n is big O of G of n. So if the numerator grows slower, denominator values grows faster, the ratio value tends to 0. On the other hand, if the ratio value goes to infinity as n tends to infinity, so that is similar to having like the other way around. You have a very large numerator divided by a very small denominator, and this is close to again a very large value, right? So for theoretical purposes we can say it is infinity. So if T of n over G of n is infinity, that means the numerator function, which is like this large value, grows faster than this denominator function, which is a very small g of n. So if you want to now relate the two, T of n and g of n, the big function is T of n function. So you write that inside the big O notation. And on the left hand side, we can say it is g of n equals big O of T of n. So always write the bigger function, the larger function, the function that goes faster, quickly, however you want to call it, inside the big O notation. And the other function goes to the left hand side. So g of n is state big O of T of n. So these are the two extreme cases. If the ratio goes to 0, it means denominator growth is larger. If the ratio goes to infinity, that means the numerator function is larger. On the other hand, if the ratio evaluates to a constant other than 0, because we already dealt the case of the ratio being equal to 0, so we are now looking at the ratio equal to constant other than 0, then that means you can say T of n, if T of n divided by G of n is a constant, we can say T of n is equal to that constant times G of n. So that means T of n and G of n pretty much go at the same rate, they are just differing by this constant. That's a factor in which the growth rate is different. So we can say T of n is this theta of G of n. Okay, so this is the rule for the limit approach. Like you will evaluate the limit of the two functions and see how the limit value and what is the limit value. If it is 0 or infinity, we will use the big O notation depending on the case, and then if it is a constant other than 0, we'll use the theta notation. So let us work it out. So you have 5n cubed plus 6n plus 2 divided by n to the power 4. So that's the f of n function, the numerator, and this g of n function that you came up with like a hypothesis. Given this f of n, what is the value of what function can I have for g of n such that f of n is big O of g of n and not equal to theta of g of n. So anything of degree greater than 3 can fit for g of n. So I assume let g of n be n to the power 4. Now we want to prove that this is a correct choice. So take the limit. So now you want to evaluate the limit. So one way is, this is just one term in the denominator, so you can divide each term in the numerator by n to the power 4. 5n cubed divided by n to the power 4 is 5 over n. 6n divided by n to the power 4 is 6 over n cubed. 2 over n to the power 4 is 2 over n to the power 4 as it is. So now you have the limit n tends to infinity, so we cannot simplify beyond this, so just let us just submit the limit. So put n is equal to infinity here, anything over infinity is 0, so each term will evaluate to 0. Infinity cube is still infinity, so n 6 divided by infinity is 0. So 0 plus 0 plus 0 is still 0. So that means this ratio evaluates to 0 as n tends to infinity. So if the ratio evaluates to 0, that means the denominator function grows faster than the numerator function. So that means we can put the denominator function inside the big O notation and then the other function on the left hand side. So 5n cubed plus 6n plus 2, which is our f of n function, is big O of n to the power 4, that's our g of n function. Okay, so let me check the video. It's okay. Any questions so far before we go to the second example? Okay, so let us do one more example on this. I have two examples. Okay, so let us take this f of n to be square root of 5n square plus 4n plus 2. So now what I want to do is find a function g of n such that f of n is state of g of n using the limit approach. So we have to read the question carefully and find out what I am asking. The first example, we have to find a function g of n that is such that f of n is only big O of g of n and not theta of g of n. Whereas in this example, I want to find a function g of n where f of n is theta of g of n. That means the g of n function should show the same rate of growth as the f of n function. So that means we have to find the degree of the f of n function first. So how to find the degree of the f of n function if it looks complicated like this, but it's actually easy to find out. So again, remember, we are always dealing the asymptotic time complexity. That means we want to see how the function grows as n tends to infinity. So that also means we can discard the lower order terms. So we can discard 4n and we can discard 2. So just look at the function inside the square root. We can discard the lower order terms, and what we are left with is with 5n square, and discard even the coefficient. So what we are left with is simply n square. And so I can say the square root of 5n square plus 4n plus 2. So let me type it out. So square root of this 5n square plus 4n plus 2 is approximately equal to square root of n square. So this is what we came up with now. Okay, we discarded the lower order terms and we discarded the coefficient. So I can say this is simply square root of n square. And square root of n square is just simply n. So this is a candidate for our g of n function. Okay, because we want something at the same rate. So n to the power 1, right? So 1 is the degree of this polynomial here, and this itself could be our g of n function. Or we can, if you find f of n grows at the rate of n, we can come up with g of n to be 2n or 3n or simply n. Okay, so because we want to put inside the g of n function inside the theta notation, so it's better to not come up with something that doesn't have any coefficient. So this n itself could be a g of n function. So now what we want to do is again use the limit approach. So we want to take the limit n tends to infinity f of n over g of n. F of n is square root of 5n square plus 4n plus 2, the given function, and g of n is n. So now n we got it from square root of n square, right? So since the numerator has n square in it, just to solve this problem easily, we can put this instead of n, we can say it's square root of n square. Okay, just to kind of do the math quickly. So now we have both the numerator and denominator square roots, so we can take like a common square root and write things together. So 5n square plus 4n plus 2 as it is divided by n square. So the only differences between these two steps is we have the whole thing inside square root. Because you have both numerator and denominator square root, you can write the whole thing in square root like this. So now you divide each term in the numerator by the denominator n square. So 5n square divided by n square is just 5. 4n divided by n square is 4 over n. 2 over n square is as it is 2 over n square. So you have to carry over the limit n tends to infinity in all these steps. So now we cannot simplify anything further below this. So substitute the limit n equals infinity. There's no n associated with 5, so 5 stays as it is. So plus 4 over n, 4 over infinity is 0. Anything divided by infinity is 0. 2 divided by n square, n is infinity, so infinity square is still infinity. So 2 over infinity is also 0. So the whole limit evaluates to square root of 5, which is a constant other than 0, and that is a rule for the limit approach. If the ratio evaluates to constant other than 0, then t of n is theta of g of n. Okay, so we can say in this case is f of n is theta of n. Now, so problems like the examples 1 and 2 are one type of problems where I'll give you one function f of n and ask you to find the other function g of n such that f of n and g of n are related either through the big O notation or through the theta notation. Now the second kind of problems in this category is I'll give you both the functions f of n and g of n and I ask you to find the most appropriate asymptotic notation to use. So that's the second type of problems. I'll give you both the f of n and g of n functions. So again, as usual, use the limit approach. So take limit n tends to infinity f of n over g of n. So in this case, f of n is n times n minus 1 over 2, g of n is n squared. That's what I've written here. So now how to simplify this? So this half is a constant in the numerator. So we could take it outside and say this is limit n tends to infinity, and then the numerator will simply have n times n minus 1, which is n squared minus n divided by n squared in the denominator. So now the n square can cancel, n over n square is 1 over n. So this is half times limit n tends to, so still we have not applied the limit. So limit n tends to infinity 1 minus 1 over n. So now you can apply the limit as infinity. 1 over infinity is 0. So 1 minus 0 is 0 times this 1 half, which is 1 half. So as n tends to infinity, we can have what? F of n or g of n is a constant here other than 0. So they can say f of n is theta of g of n. So that's the most appropriate asymptotic notation. Okay, so we'll stop and save this video.